logarithm output. If I take this first number and do the log of that number, that means what exponent goes on 10 to get this number? 10 to the negative 4 equals that number, so that number would translate to negative 4. The next number, input it as the argument of the log, and I get negative 3. And then as I continue to sub these numbers in, notice when I take this set of very small and very large numbers, do the log of each of them, I get this set of numbers, which would be a lot easier to work with. And there are a few formulas that take advantage of the fact that a logarithm can output these nice manageable numbers. For example, the pH formula is equal to negative log of the hydronium ion concentration. How is this formula used? Well, pure water has a hydronium ion concentration of 1 times 10 to the negative 7. So really small number, 0.0000001. What we do is we calculate the pH of pure water by doing the negative log of its hydronium ion concentration, 10 to the negative 7. And then evaluating this is just what exponent goes on 10 to get 10 to the negative 7? Well, that's negative 7. So we do negative 7, which is just 7. Pure water is neutral. So this 7 is actually unitless. It's just a way of taking a hydronium ion concentration, which does have units in moles per liter, but converting that really small number into a number that is easier to analyze. And there are lots of other formulas which take advantage of the fact that logarithms can do that with really small or really big numbers. For example, there's a formula for sound levels. Measuring sound in decibels, their difference in their sound levels is equal to 10 times log of the ratio of their sound intensities. Let me make a little bit more room and then talk to you about a logarithmic scale on a graph. Sometimes logarithmic scales are used when graphing data with a very large spread. When graphing data, or functions, usually you use a linear scale, but there's another scale you can use called a logarithmic scale. Sometimes a logarithmic scale is used when graphing data with a very large spread of values. For example, let's look at the function y equals 10 to the power of x. If I were to make a table of values for that function, I'll choose x values from negative 3 to 3, and if I calculate the y values by doing 10 to each of those exponents, I get the following y values. Now let me try and graph these points to show what this function looks like. Your initial instinct would probably be to use a linear scale. So let me make a little bit of room and we'll do that. If we zoom in on this graph, notice that the scale I made, on the y-axis, the numbers are going up by a common difference each time. Or another way we should say that is that measurements that are an equal distance apart, like 10 and 20, and 50 and 60, those are an equal distance apart, their difference in values is equal. They both have a difference in values of 10. And now if I were to take all of these points from the table and try and get them onto this graph, these first few points are going to be very difficult to plot because they're so small. And this point at the end is so big, it's not even going to fit on the graph. But I'll do my best to plot them. And if I connect them to show what this function looks like, I get this exponential curve. And there actually is a horizontal asymptote right along the x-axis at the line y equals 0, so I'll draw that in as well. But me showing you this linear scale for this function is just to point out that seeing the difference in these values is very difficult to see. And because these differences are so big, we're going to stop being able to get points that fit on our graph. So there's actually a different type of scale we could use for a function just like this, and it's called a logarithmic scale. So let me make some room and do another graph. Now let me zoom in and label some points on here. So this logarithmic scale I made, there's a few things I want to point out. First of all, pairs of points that are an equal distance apart, like 1 and 10, or 100 and 1,000, they're an equal distance apart, but their difference is not equal. This difference is 9, but this difference is 900. The difference isn't equal in a logarithmic scale, but the ratio of the numbers is equal for points that are equidistant apart. So those points that are equal distance apart, the ratio of 10 divided by 1 is 10, and the ratio of 1,000 divided by 100 is 10. So in a logarithmic scale, these numbers are going up by a factor of 10 each time. Multiply by 10, you get to the next number. And it doesn't have to be by 10, but that's a common one that is used. Another thing to know that if you were to do the common logarithm of each of these numbers, the values that you would get would have an equal difference, right? Logarithm of this would be -3, then -2, then -1, then 0, then 1, 2, 3, 4. The other thing you need to notice is I didn't draw in an x-axis because that would imply we were at a y value of 0. And if you think about it, what would be the next y value as we go down? Well, we would just be adding another 0 in the decimal place before the 1. So it would be 0.0001. And then the one after that would have 4 zeros, then the 1, and so on. So the numbers will just keep getting closer and closer to 0, but they will never get there. So for that reason, we can't draw in an x-axis. And when I plot each of these points on this logarithmic scale, let's watch what they look like. They actually form a perfectly straight line, and I was able to plot every single point that is in that table on my graph here. Must know number 10, the derivative of a logarithmic function. Let me start by showing you the derivative rule for the derivative of log base b of x. The derivative rule tells me this would be equal to 1 divided by x ln of b. So you take the argument of the log, it goes here, and you take the base of the log, and that becomes the argument of the natural logarithm. And now let me show you how this would work if we had a composite function. So if we wanted the derivative of log base b of f at x. So if the argument of the logarithm is a function of x, you need the chain rule, which would tell you that you would do 1 divided by the argument, which is f at x, times the natural logarithm of the base, but that has to be multiplied by the derivative of the inside function. So it would have to be multiplied by f prime of x. So an example where we would need this is if you wanted to find the derivative of 2 times log of 3x squared. So the first thing, I could use the constant multiple rule. I have a constant factor. I could just move that in front of the derivative. And because the argument is a function of x, I need the chain rule. So this would be equal to 2 multiplied by 1 over the argument, which is 3x squared, times the natural logarithm of the base of the log, and I don't see a base, so it's the common logarithm, so the base is 10, and that has to be multiplied by the derivative of the argument. The derivative of 3x squared is 6x. And then this could be simplified. I've got a 6 divided by 3, that's 2, and this x can cancel with one of those x's. So the final answer, in the numerator, there's 2 times 1 times 2, that's 4, and in the denominator is just x times ln 10. So there you go. Hopefully that video has made you more confident in your understanding of logarithms. Let me know in the comments what you want me to do a video about next.